In our last videos, we introduced the concepts of conservation and symmetry, and observed how they were linked through Noether's theorem. In particular, the kinds of events that can occur in nature are limited by a set of rules, namely that quantities like energy, momentum, and charge cannot change in value even as a system undergoes a dynamic change in its overall state. These laws of conservation result from the fact that the laws of nature are invariant or symmetric under certain kinds of transformations, such as translations through time and space or various rotations. Through Noether's theorem, we can determine mathematically what conserved quantity is associated with each symmetry of a system. This is a truly powerful idea. In physics, a theory, meaning a description of a large set of different systems in nature, is characterized by the symmetries it possesses. As we've observed, the symmetries of the theory allow us to define the conserved quantities of the system it describes. These conserved quantities, in turn, determine the possible states the system can realize. If we know the symmetries of a theory, we therefore know quite a lot about the possible things the theory can describe. To understand what I mean by this, imagine you're decorating a room. Before you start decorating, you need to determine a few important details about that room. For instance, its dimensions, its length, its width, and its height. These numbers are the quote-unquote conserved quantities of your project. They can't change unless you fundamentally alter your objective. They define the set of possible rooms you could design. You can't add any decoration or set of decorations which are too large to fit in the room. So, when we say that a theory is characterized by the symmetries it possesses, we're simply saying that the possible things the theory can describe are confined to the space defined by the conserved quantities associated with those symmetries, just like how the possible ways we can decorate any room are limited by the size, length, width, and height. In this way, we can think of any theory as a room where we can place different systems whose dimensions are determined by its symmetries. At its most basic level, the Standard Model is nothing more than a theory of physics which describes any system comprised of the particles and interactions contained in the Standard Model. So, the first step towards truly understanding the Standard Model is simply to understand the quote-unquote dimensions of the room it describes. In this and the next video, we will show that the dimensions of the Standard Model are in fact the familiar quantum numbers we introduced in our first videos about the Standard Model. To reach this amazing fact, we must first determine the symmetries that the Standard Model possesses. In fact, the Standard Model, like any theory of physics, contains two kinds of symmetries: space-time symmetries and internal symmetries. We'll get to space-time symmetries in a bit, but for now we'll shift our focus to internal symmetries. Internal symmetries refer to symmetries arising from transformations which change the quantum fields used to describe our theory. The Standard Model has three internal symmetries with the scary-sounding names U1, SU2, and SU3. Oh boy, that sounds really complicated. Only, would you believe me if I told you that we've already described all of the ideas necessary to understand what these weird names mean? Indeed, the internal symmetries of the Standard Model are simply three different kinds of rotations. That's right, just like how when we rotate a circle, its image does not change, when we rotate the quantum fields of the Standard Model in three different ways, the fundamental laws of physics do not change. All that remains is to describe what exactly it means to rotate quantum fields and what these three different kinds of rotations are. So, let's get started. To start, let's think about a slightly more quantitative description of what a rotation is. A rotation involves taking an object with multiple components, for instance a location measured from some origin point consisting of displacements along the x and the y axes, and mixing those components without changing the size of the object. In the case of a location, this means that a rotation may change how far along the x-axis or how far along the y-axis that location appears to be, but it cannot change the total distance of that location from the origin. Now, remember that a quantum field is essentially just a way of communicating the number of a given particle at any point in space and time. As such, we can think of the quantum field as a series of lists, one for each point in space and time, containing the name and amount of each particle present at that moment and place. A rotation of the quantum field then simply involves mixing up or scrambling the content of those lists, like the components of the location in the example before, but not changing the size of the list. In this case, size refers abstractly to the total number of particles present at any given point. The laws of physics do not care about the order of the list, they only care about the particles that are present. Hence, the laws of physics are invariant under such rotations of the quantum fields. Operationally speaking, this means that if we write down the Lagrangian for some particles and rotate their quantum fields, the Lagrangian will turn out to be unchanged. To understand intuitively why this should be the case, imagine you're a teacher and possess a list of names of students in your class. Typically, we might write these names in some kind of an order, for instance, alphabetically. But imagine we rotated the elements of this list. That is, we scrambled up the order of the names so that it was no longer alphabetical. Indeed, this changes the way that the list looks. But does it change the class that you're teaching? Well, of course not. The order of the names is different, but the students who are in your class has not changed. In this way, you can think of a rotation as being like a change of perspective, but not a change of subject. Like turning your head around to get a better look at something. The way you look at something can change the way it looks, but it cannot change what you're looking at. Awesome. Rotating quantum fields just means jumbling up the description of the particles being represented, but not changing the total number of particles. Doing so changes the quantum fields in such a way as to leave the Lagrangian describing them invariant. So, now what are these three different kinds of rotations? That turns out to be a slightly more complicated question. For the time being, it'll suffice to think about these different rotations in terms of the number of quantum fields that they rotate. U1 rotates a single quantum field, SU2 rotates a pair of quantum fields, and SU3 rotates a trio of quantum fields. So, there we have it. The dimensions of the standard model are, in some sense, no more complicated than the fact that we can rotate a circle and not change the way that it looks. Of course, there are still many questions remaining. Which quantum fields are rotated by each of our three transformations? Why do we only go up to 3? And how can we unify these 3 different symmetry groups? Fear not, my friends, for the answers to these questions and more await us in future videos. For now, however, we've determined that the internal symmetries of the standard model are, in some sense, no more complicated than the symmetries of a circular geometry. In the next video, we will see that these symmetries are hiding a very deep insight about the structure of the standard model, which will make very clear the conserved quantities that they generate. But, for now,